Welcome back. Today we will discuss the addition, subtraction, multiplication, and division of mixed numbers. Last class, we introduced the concept of a mixed number as a special way to denote or write measurements. Start here. Welcome back. Today we will discuss the topic of mixed numbers, and specifically we'll talk about the addition, subtraction, multiplication, and division of mixed numbers. Last class, we introduced this idea that mixed numbers are a special way of denoting an improper fraction such that when you actually go to measure out a specific quantity, you can actually do that with the measuring tools that are available to you. And we discussed how in the past, it was very important prior to the invention of precision tooling and prior to the invention of, say, digital calculators and calculation devices, or electronic and or digital computing, where you've got digital sensors that are super accurate. It would have been very hard to measure certain types of quantities with the tools that were available. And so instead, you just had to make do with what you had at your disposal. And to that end, a lot of the mathematics was geared towards facilitating being able to perform certain operations and or write numbers in a certain way so that you could do something useful with them. Okay, so you may have a mixed number such as 3 2/5. And at some point, you might want to, say, add 4 1/5. And the question, of course, is, well, what is this actually equal to? And what's interesting here is there are a couple of different ways that you can interpret this statement. The first, and probably the easiest, is to just consider the definition of a mixed number. When you write 3 2/5, you're literally saying 3 plus 2/5. And when you write 4 1/5, you're literally saying 4 1/5. And so I use parentheses in this instance to denote one specific number or one chunk of a number. So 3 2/5 as being this 3 2/5 thing, mixed number above, and the 4 plus 1/5 as denoting the 4 1/5 mixed number above. Now, what's interesting is, according to the associative law, you can, of course, remove the parentheses anytime you have a string of numbers that are added together, such as the following. So we'll go ahead and remove the parentheses in this instance. And at this point, we can use the commutative law to group our whole numbers together. And now you've got 3 plus 4, which gives us 7. 2/5 plus 1/5. That, of course, gives me 3/5, just like 2 apples plus 1 apple gives me 3 apples. And we can then go ahead and write this back as a mixed number, 7 3/5. And that's all we have to do. Now, it's a lot of steps to do this process. If you're going to do it by hand using just the rules of algebra, it is, in fact, kind of a laborious process, but you will always be left with the correct answer. So, of course, when in doubt, I would always recommend students go back to the basics, go back to your definitions, understand the rules of algebra, and write everything out one step at a time, because it will always result in a correct answer. Let's try another one. Suppose you've got 2 1/7 plus 3 4/7. What would this equal to? Well, here again, you could write 2 1/7 as 2 plus 1/7. And we could write 3 4/7 as 3 plus 4/7. And of course, we can then remove the parentheses. and use the commutative law to group our fractions together. 2 plus 3 gives me 5. 1/7 plus 4/7 gives me 5/7. And we're now left with our mixed number, 5 and 5/7. Excellent. Again, it's a decent number of steps, so is there potentially a better way? And of course, the answer is yes. If you look at the pattern here, we started with 3 and 2/5. And of course, we added this with 4 and 1/5. And what we saw was this was equal to 7 and 3/5. It's instructive to, of course, highlight in green the fraction so you can kind of see the pattern. You'll note that, first of all, the bases are the same. And we know that for fractions, if they have the same denominator or the same base, then what it means is you can add across the top. So you've got this 2/5 plus 1/5, and then past the equal sign, you'll see that we have 3/5 next to the 7. And of course, for the whole number terms, we had 3 added with 4, and of course, that always gives us 7. So the pattern here is simply that as long as you're adding mixed numbers where the fraction bases are the same, then of course you can simply add the whole numbers and add across the numerator of the fraction. Now, of course, this is contingent upon the denominators being the same. When the denominators are not the same, you would of course have to find some sort of a common denominator, at least for the fractional terms. However, even with the second problem, if you look at 2 and 1/7 added with 3 and 4/7, you'll see that if we had just added the whole numbers, the 2 and the 3, and if we had just added the fractional pieces, the 4 and the 1, you would be left with the correct answer, 5 and 5/7. And this just further demonstrates this idea that as long as we have mixed numbers where the fractions have the same denominator, we can, of course, add the fraction pieces together and add the whole numbers pieces together, and you'll be left with your answer. Okay, but let's see an example where that's not the case, right? So suppose you had 3 and 4/5 added with 6 and 2/7, and you're like, what is this equal to? Okay, well, algebraically, what we would be dealing with is 3 plus 4/5 plus 6 plus 2/7, right? And we could then remove our parentheses. You'd have 3 plus 4/5 plus 6 plus 2/7. Students, remember, you can't use the commutative law without removing the parentheses. If I see you using commutative law before you remove your parentheses, it's going to be points docked. You can't do it. I mean, you can do it, but it's algebraically incorrect to do it. So I don't want to see it on an exam. Nevertheless, at this point where we've got a sequence of terms all added together, you would similarly just simply add the whole numbers with whole numbers and the fractions with fractions. 3 plus 6 gives you 9, and you have 4/5 plus 2/7. Well, for 4/5 and 2/7, I can't really add that with the 9 as it currently stands, nor do we want to. But we could, of course, find a common denominator for 4/5, which would, of course, be the same thing as multiplying by the opposing base, since both numbers are prime, and the LCM would be 35 anyways. So we're going to take our first fraction, 4/5, and we're going to multiply by 7/7, because that's the opposing base. And we'll take our second fraction, 2/7, and we'll multiply by 5/5, because that's its opposing base. 4 times 7 gives us 28. 5 times 7 gives us 35. Add it with 7 times 5, which is 35. 2 times 5 gives you 10. Add that with 9. And you'll have 9 plus, what is this, 38 35ths. And here's the little thing about simplifying these fractions. At this point in time, this 35 will actually go at least once evenly into 38, and you should be left with 3 left over. And so the trick of doing these problems is just being able to perform the adjustment that you need whenever you're presented with a situation that calls for you to simplify this improper fraction here. 35 divides 38 once. You're going to have 3 remainder, because if you do 38 minus 35, you're going to get a 3, meaning if you went one time into 38, you'd have 3 remainder. So you can write 1 plus 3 over 35 to represent the division process there. And finally, we can add 9 with 1, giving us 10, and you'll have 3 over 35 left over. Sorry, I'm writing a little bit with a little bit of a smudge there. So let's go to the next page. We will have 9 plus 1 gave us 10, and 3 over 35 is remaining. So we have 10 and 3/35. Okay. Is there a faster way? The answer is kind of, sort of. If we had simply focused on trying to simplify these fractions, or not simplify, but find a common denominator for each of the fractions, we could have taken 4/5 and say multiplied by 7 over 7, and we could have taken the 2 over 7 and multiplied by 5 over 5 on the top and the bottom. And what you would have gotten is you would have gotten 7 times 4, which is 28. 5 times 7 is 35. 2 times 5 is 10. 7 times 5 is 35. Now, we could have added the whole numbers, 6 and 3, giving us 9. And the fractional pieces, so you'd have 28 plus 10 over its denominator, 35. This would still give you the 38 over 35. And at this point in time, you just simply do the division process, which would give you that 1 and 3 over 35, or simply 10 and 3/35. Okay. Regardless of whether we want to do things in an algebraic manner or whether we decide to do things using the mixed fraction rules, it really doesn't matter, as long as we watch our steps and we understand the key idea behind what the mixed number is trying to represent. And with subtraction, things aren't that much different. The only, I guess, nuance with fractions is you do have to watch your signs. You may have, say, 2 different negative numbers, and of course, negative and negative becomes addition. So you do have to watch your signs. However, as long as you do that, subtraction is very similar to addition. So suppose you got 10 and 3/5, and you're subtracting 3 and 2/5. Well, what would this equal? Okay. Well, very literally, you've got 10 plus 3 over 5. And we're going to be subtracting off from that 3 and 2 over 5. Now, what this amounts to physically is you've got 10 plus 3/5. But we'll be subtracting both the 3 and the 2/5. This is a little weird for students, but you're subtracting the whole quantity, 3 and 2/5. So we're not just subtracting the 3 from the 10 and 3/5. We're subtracting the 3 and 2/5 from 10 and 3/5. So both need to have subtraction symbols. Okay, it's a little bit of maybe some abstraction there to wrap your mind around, but just think about it and you'll come to agree with that understanding. Okay, because we are subtracting off the 2/5 as well, not just the 3. Now, just like before, you can use the commutative law as long as you very carefully account for that negative symbol in front of the 3. And of course, we will line up our fractions with one another. So you'll have 3/5 minus 2/5. 10 minus 3 gives you 7. 3/5 minus 2/5 gives you 1/5. And so your answer is 7 1/5. Pretty much all you have to do. The easier way to go about this is to simply subtract the whole numbers from one another and make some sort of an adjustment if need be. So we would take, say, 10, we would subtract 3, that would give me 7. And I would subtract my numerators from one another. So I'd say take 2 away from 3 because both of the fractions are over 5. Now we're going to have 7, 3 minus 2 gives you 1. So 7 1/5. Here's where things get kind of weird. Suppose we have 5 1/4 minus 3 3/4. What would this be equal to? Okay, so algebraically, you should write out 5 plus 1/4. And of course, we're subtracting from this 3 3/4. After accounting for the subtraction symbol, you'll be subtracting out the 3/4 and the 3, and you'll have 5 plus 1/4. Moving your terms together, you have 5 minus 3. But now we have 1/4 minus 3/4. 5 minus 3 gives you 2. 1/4 minus 3/4 gives us negative 2/4. Okay. Which also equals negative 1/2. But then we've got the situation. What is 2 minus 1/2? Well, if we think about 2 minus 1/2, here's 2 pieces. And if I split one of my pieces in 2 and I chopped off 1/2, I would have 1 1/2 remaining. So we already know that this answer needs to be 1 1/2. But what's going on? Well, what's happening here is very, very similar to what happens when you're using the subtraction algorithm and you encounter some sort of a number which cannot subtract another number in the row below. So for example, you might have something like 34 minus 18. Well, if we were to use this subtraction process, we would say 4 is smaller than 8, and you can't have a number in the bottom row that's bigger than the number in the top row. So you borrow a 10 from the column over. So now your 4 becomes a 14, and you do 14 minus 8, which is a whole different story. And so 14 minus 8, of course, would give you 6. And because you borrowed a 10, your 3 now becomes a 20. Or your 3 becomes a 2, rather. So you do 2 minus 1, giving you 1. The same thing is really happening here. You're borrowing from a 1, basically, if you think about 1 as being the same thing as a 2/2, then you're taking away one piece from the 2. So you would have 1 plus 2/2 minus 1/2. And when you do the subtraction operation there, you get 1 plus 1/2. And that is effectively what's happening here. Now, it is a little bit weird trying to wrap your mind around, like, when do we do that borrowing operation? Okay, so that is kind of the strange part. However, one thing you should know about whether it be we're adding these mixed number terms, or we're subtracting these mixed numbers terms, is just like with the addition and subtraction algorithm, you can actually line up your numbers. So if you do 5 and 1/4 minus 3 and 3/4, and you just look at it column-wise as column-wise subtraction, just as though we were subtracting 18 from 34, then what's happening here is you've got a 5 minus 3, which gives you a 2. However, because in this row, you've got 1/4 minus 3/4, you have to, before you can do that subtraction operation in the second column, it's almost like you've got to borrow a 1 from the 5. And then now you would have a new problem if you added 2/2 with 1/4. I'm sorry, not 2/2, but 4/4 with 1/4. So 4/4 plus 1/4 would give you 5/4. And you've got a new problem, 4 and 5/4 minus 3 and 3/4. Well, now if you were to column-wise subtract, 5 minus 3 gives you 2 exactly. 4 minus 3 gives you 1 exactly. Okay? And here's the deal. 1 and 2/4 is exactly the same thing as 1 and 1/2 when you reduce the fraction. Okay. Let's try another one. Let's do 7 and 2/3 minus we'll do 7 and 1/3 minus 4 and 2/3. Okay. Just as before, if we kind of column-wise subtract, we're going to have 7 and 1/3 minus 4 and 2/3. And what we're going to do here is we're going to start in the rightmost column. Of course, we're going to try to subtract the 2 from the 1, and you can't do that. So we would have to borrow from the 7. And because our base is 3, it means we need to add 3/3 to 1/3, and the 7 would become a 6. Making this adjustment, 1/3 plus 3/3 gives me 4/3. So we now have 6 and 4/3 minus 4 and 2/3. So if we're doing our column-wise subtraction, 4/3 minus 2/3 should give me 2/3. 6 minus 4 should give me 2. So our answer would be 2 and 2/3. One last example. We'll say we have 8 and 4/7 minus 2 and 6/7. Using the column-wise subtraction strategy, you're going to line up your 8 and 4/7. You would also line up your 2 and 6/7. Looking to this rightmost column, you're going to subtract 6 from 4, and of course you can't subtract 6 from 4, so you need to borrow a 1 from the 8. Since your fraction is denominated in sevens or sevenths, you're going to need to add a 7/7 to the 4/7. 7 plus 4 gives you 11, so now you've got 11/7, and when you borrowed a 1 from the 8, that becomes a 7. So you've got 11/7 minus 2 and 6/7. 7 minus 2 gives you 5. 11 minus 6 should give you 5. And the 7 is in the denominator, which remains unchanged. This is basically, in my opinion, probably the fastest way of performing the subtraction operation. But just remember, guys, if it's too cumbersome to learn a new method of performing subtraction using the column-wise subtraction with fractions, always just resort to what you know in terms of algebra and the rules of basic numbers. So you could always go back and write out your 8 plus 4 over 7 minus 2 plus 6 over 7. And just go through things the long way. There's no problem writing things out. You'd have 8 plus 4 over 7 minus 2 minus 6 over 7. You get 8 minus 2 plus 4 over 7 minus 6 over 7. You're going to get 8 minus 2 is 6. 4 minus 6 gives you -2. So you have -2/7. Breaking up the 6, i.e. borrowing a 1 from the 6, that gives you a 5 and 7 over 7. 7 over 7 minus 2 over 7 gives you 5 over 7. And our answer is as follows. It's just that you have to remember what to do at this step, whereas it becomes obvious if you were to try to column-wise subtract that you can't take 6 away from 4. And so that you then have to borrow from the next column over, just like you would in regular subtraction. So if we understand the idea of regular subtraction, where we're borrowing 10, we're really not doing anything different. The only thing we have to remember is whatever the denomination is for our fraction, whatever our denominator happens to be, that's what we have to add on both the top and the bottom to our fraction if we happen to borrow from the next number over. Okay. Of course, there is in fact an easier way of doing these problems, and that would be to just convert back to an improper fraction, do the subtraction operation there, and then convert to a mixed number if you want the answer as a mixed number, right? Instead of doing all of this borrowing nonsense and having to worry about whether or not we make a mistake with borrowing and keeping track of all of these fractions, blah, 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 blah. It seems like a lot of work to me. Another recommendation or another method of doing either addition or subtraction of mixed numbers would be to first convert back to an improper fraction, do the addition or subtraction there, and finally, depending on if you care to have a mixed number as a answer, you can always convert back. So as an example of this, to convert 7 1/3 to a improper fraction, you would of course multiply 3 with 7, giving you 21, and you would add it with 1. So you'd have 22 over 3. You would do the same thing for 4 2/3. You'd multiply 3 with 4, giving you 12. And 12 plus 2 is 14. So you'd have 14/3. Well, 22 minus 14, that's some basic math, right? Got to borrow from the 2, giving you 12. 12 minus 4 is 8. So you'd have 8/3 remaining. 3 goes into 8 2 times with, and of course, how many times does it divide 8? Well, 3, if you go into 8, 3 goes twice in 8, 2 times 3 gives you 6, and if you subtract, you get a remainder of 2. So we can write this remainder of 2 as being 2/3 that is in front of the whole amount that we were able to divide 3 into that 8 term. And so, in my opinion, this is also a very fast way of being able to obtain these mixed number expressions. And frankly, I always get a correct answer. Before I really mastered how to do the addition and subtraction of mixed numbers, I'm going to be honest with students, I would always simply convert to an improper fraction, do my math there, and then convert back into a mixed number at the end of the day. And yes, at the time when I was going to school, I would get points docked because the teachers would insist that I use a specific method and I learn a specific method. And I really didn't understand the mixed numbers. And of course, they were docking you for not understanding the mixed numbers. Go figure. So for me, I would always have to just do things in one specific manner that made sense because, that's kind of just the engineering mindset there. You do what makes sense. You do what works for you. Not everything works for everyone. So just pick a method that seems to make sense, figure out how to use that method, and then stick with it for all of these problems. Okay, that would be my best advice to students in this section. Similarly, for an addition problem, just looking at this 3 4/5 plus 6 2/7. If you had converted to an improper fraction first, you do 3 times 5, 5 times 3 rather, which gives you 15. 15 plus 4 gives you 19. So you'd have 19/5 plus 6 times 7 gives you 42. 42 plus 4 gives you, I'm sorry, 42 plus 2 rather gives you 44. So you'd have 19/5 plus 44/7. Then you'd have to add together. Now, even though this looks nasty, okay, we can indeed do multiplication. So you would just have to do the multiplication of 44 with 5/5, and I'm sorry, the 44/7 with 5/5, and the 19/5 with 7/7. So you'd have to go to the side of your page. 7 times 9 gives you 63, carry the 6. 7 times 1 is 7, plus 6 gives you 13. You should have 133 all over 35, plus 5 times 44. 5 times 4 is 20. Carry the 2. 5 times 4 is 20, plus 2 gives you 22. So you got 220/35. Add everything together. We've got 133 plus 220. 3 plus 0 gives you 3. 3 plus 2 gives you 5. 1 plus 2 gives you 3. So we got 353 all over 35. Okay. And of course, if we wanted a mixed number answer, that would be just fine, right? But if we don't want to mix, I'm sorry, if we wanted an improper fraction answer, rather, that would be what we have here would be just fine. But if we wanted a mixed number answer, then we've got to do a little bit of nasty division problem. It's not too bad. We can do 35 into 353. You basically have to guess how many times 35 goes into 35. Of course, it only goes once. 1 times 35 is 35. You're going to subtract, you get 0, and have a 3 remaining. Well, not necessarily 3 remaining, but 35 doesn't go any times into 3. You would, in fact, get a 3 remainder. So what is 353/35? Well, we found that we have 10 whole pieces and 3 remaining from 35. And that was indeed what we obtained in our previous answer, right? We got 10 and 3/35. So if you feel confident with your multiplication and division operations, and I don't see why students would not at this point feel confident in doing that, by all means, convert to an improper fraction, do the math using your regular multiply by opposing base method, using the finding an LCM in order to find a common denominator, and then at the end of the day, convert back to a mixed number if the homework asks for a mixed number answer. In the next lesson, we'll discuss the topic of multiplication and division of mixed numbers. Take care, guys.